Let's take a look at Chapter 2, Section 7, where we're looking at inverse functions. Here are some of the objectives. We want to verify inverse functions, find the inverse of a function, use the horizontal line test to determine if a function has an inverse function, use the graph of a one-to-one function to graph its inverse function, and find the inverse of a function and graph both functions on the same axes. So those are some of the objectives of this section. We want to start by defining the inverse of a function. If f and g are two functions such that f of g of x is x for every x in the domain of g, and g of f of x is x for every x in the domain of f, the function g is the inverse of the function f and is denoted as f inverse. And so this way of writing f inverse looks as if we're writing f to the power of -1. That notation for inverse looks like an exponent of -1, but given the context of the problem, you'll understand that that's not a power of -1, but represents the inverse of our function f. So f of f inverse is x, and f inverse of f is x. So the domain of f is equal to the range of f inverse, and the range of f is equal to the domain of f inverse. That's what we mean by vice versa. So these are things that have to be true if two functions are inverses. So we have a vertical line test that allows us to see whether or not a relation is a function. Now we want to talk about a horizontal line test. And this is actually a test we do on a function to see whether or not the function has an inverse that is also a function. So a function f has an inverse that is a function, and remember we refer to that as f inverse, if there is no horizontal line that intersects the graph of the function f at more than one point. If a function passes the horizontal line test, we say that the function is a one-to-one function. So if a function is a one-to-one function, its inverse is also a function. So let's take a look at these two graphs, both graphs of a function, and we want to determine whether or not the function is a one-to-one function. Now remember, if there's just one line that touches the graph, which is horizontal, one horizontal line, which touches the graph in more than one place, then the function is not a one-to-one function. All right, so notice here there are actually many horizontal lines that touch this graph more than once. So imagine that's a line I just drew. Having a little trouble drawing straight. But the point to notice is that that line touches the graph in more than one place. Okay, here I inserted a better line, but notice how the point here is that this line touches the graph in more than one spot. So that would indicate that this is not a one-to-one function. All right, so 1a is not a one-to-one function because I do touch this graph with a horizontal line in more than one place. Now, if I look at B, I'll notice that there is no horizontal line that's going to touch this in more than one place. When I look over here, I see that it has what looks like y equal to 1 as a horizontal asymptote. I notice, though, that this is not horizontal. This portion of the graph is not horizontal. It actually represents something that every time you move slightly to the right, the graph is actually slightly moving up. And it keeps getting closer and closer to y equal 1 without actually touching it. So no horizontal line will touch this graph more than one time. So this is a one-to-one function. Okay, so here we do have a one-to-one function on 1b. On 1a, we do not have a one-to-one function. So what this tells me, 1a could have an inverse, but that inverse is not going to be a function. Whereas b has an inverse that is a function. Sometimes I want to show that two functions are inverses. Here I have f and g, and I want to show that they're inverses. One way I could discuss this is the idea of using composition cancellation equations to verify that f and g are inverse functions. And that basically means I'm going to show that f of g of x equals g of f of x, which equals x. So that's actually what I'm going to show in expressing that these two functions or proving that these two functions are inverses. So f of g of x means I'm going to make g the input to f. Well, f takes its input, whatever you put into f, you put that input in the numerator. So 5x over 1 minus 3x is my numerator. And in the denominator, you put 5 plus 3 times whatever your input is. And in this case, that's 5x over 1 minus 3x. All right, so this is an example of a complex rational expression. And I have a minor fraction in the numerator and a minor fraction in the denominator. And they happen to be the same fractions. So I'm going to multiply the numerator and the denominator by the denominator of this rational minor fraction that appears twice in the expression. Now, realize what I'm doing is multiplying by 1. Any non-zero number over itself equals 1. And so when I multiply a number by 1, I don't change its value. So when I multiply 5x over 1 minus 3x times 1 minus 3x, I merely get 5x. When I multiply 5 times 1 minus 3x, I get 5 times 1 minus 3x. And I have plus 3 times, and when I multiply 5x over 1 minus 3x times 1 minus 3x, I simply get 5x. So I have 5x over 5 minus 15x plus 15x. And I see that in the denominator, minus 15x adds with 15x to give 0. And I have 5x over 5. And these 5's divide out. 5 divided into 5 is 1. And 1 times x is x. Okay, so the first composition worked. F of g of x is indeed x. Now let's see what happens when we do the composition g of f of x. So I'm going to take f and I'm going to make that the input to g. I'm going to get a similar type of complex rational expression. So what g does is it takes its input and it multiplies it by 5, and it puts it in the numerator, and in the denominator puts 1 minus 3 times whatever I have put into the function. In this case, my input is x over 5 plus 3x, which is what the function f equals. So obviously, this again is a complex rational expression. And what I'm going to do is multiply. I have two identical minor fractions. So I have the denominator of each rational fraction, minor fraction, as 5 plus 3x. So if I multiply the numerator by 5 plus 3x and the denominator times 5 plus 3x, I'll clear the minor rational expressions or minor fractions out of the problem. Okay, so I continue with my work. All right, and I see that what happens when I multiply 5 times x over 5 plus 3x times 5 plus 3x, I simply get 5x. And when I multiply 1 times 5 plus 3x, I simply get 5 plus 3x. And when I subtract 3 times x over 5, when I subtract 3 times x over 5 plus 3x and multiply that term by 5 plus 3x, I simply get a minus 3x. I decided, at least on this one, I want to insert one extra step just to make sure what we're doing here is clear. I want to actually show this multiplication of each term. So I want to actually show it just to make sure that this product is clear. You're multiplying the numerator only by 5 plus 3x. And there's only one term in the numerator, so you only have to multiply that single term. I went ahead and multiplied 5 times x over 5 plus 3x. So in the denominator, each term there gets multiplied by 5 plus 3x. So I multiply the 1 by 5 plus 3x, the minus 3x over 5 plus 3x also gets multiplied by 5 plus 3x. So I just wanted to make sure that at least for this second composition, g of f of x, you see this step. I didn't show this step in the first calculation that I did when I calculated f of g of x. So the point is, you rid the problem of the minor fractions, and now my numerator is simply 5x, and you've done so legally because you've only multiplied by 1. And when you multiply by 1, you don't change the value of what you were multiplying. And I simply have a minus 3x left here. So in the denominator, 1 times 5 plus 3x is 5 plus 3x. Minus 3x over 5 plus 3x times 5 plus 3x is simply minus 3x. And notice that 3x minus 3x is 0. And I am left with 5x over 5. And 5 divided by 5 is 1. And 1 times x is simply x. So I've actually shown that f of g of x equals x, as does g of f of x. Therefore, f and g are inverses. That's what I'm able to conclude.